Hello, everyone. Welcome to the Analog Electronic Technology course. Today, we'll explore power transistors. While delivering power to the load, the transistor itself also dissipates part of the power. The power dissipated by the transistor results in a rise in junction temperature. If the junction temperature exceeds a certain limit, the transistor may be damaged. In BJTs, most of the voltage drop occurs across the collector junction. The combination of this voltage and the current flowing through the collector causes power dissipation at the collector, which generates heat in the device. Therefore, collector power dissipation is commonly used as a measure of a BJT's total power dissipation. The working principle of high-power BJTs is exactly the same as that of low-power BJTs. The only difference is that the PN junction area is much larger in high-power devices. To improve heat dissipation, power BJTs typically adopt special packaging techniques, such as ensuring good thermal contact between the collector substrate and the metal case, so that heat can be efficiently transferred to a heat sink. The relationship between the maximum allowable power dissipation PCM of a power BJT, the total thermal resistance RT, the maximum allowable junction temperature TJ, and the ambient temperature TA is given by TJ minus TA equals RT times PCM. The total thermal resistance RT includes the thermal resistance from the collector junction to the case, the thermal resistance between the case and the heat sink, and the thermal resistance from the heat sink to the surrounding air. It is measured in degrees Celsius per watt. When the maximum junction temperature and ambient temperature are fixed, the smaller the thermal resistance, the greater the allowable power dissipation. The heat sink and its surface area can significantly affect the thermal resistance. In practical applications, it's often observed that even when the power dissipation of a power BJT does not exceed the allowable PCM, and the transistor case doesn't feel hot, the device may suddenly fail or its performance may degrade significantly. This type of damage is often caused by a phenomenon known as secondary breakdown. In general, secondary breakdown is an effect influenced by current, voltage, power, and junction temperature. The physical mechanism is widely believed to be due to non-uniform current distribution across the junction area, which causes localized overheating and results in thermal breakdown. This is closely related to the manufacturing process of the BJT. To ensure the safe operation of power transistors, the risk of secondary breakdown must be carefully considered. Therefore, the safe operating area, SOA, of a power transistor is limited not only by the maximum allowable collector current ICM, the maximum collector emitter breakdown voltage VBRCE, and the maximum collector power dissipation PCM, but also by the secondary breakdown limit curve. The SOA is shown in the diagram. Clearly, when secondary breakdown is taken into account, the safe operating range of a power BJT becomes narrower. To meet the demands of high-power applications, vertically structured MOSFETs were developed in the 1970s and 1980s, significantly increasing the output power capabilities of MOS devices. These include V-groove MOSFETs and double-diffused MOSFETs, both of which have gained widespread use due to their excellent performance. The V-groove vertical MOSFET, commonly referred to as the VMOS, uses a heavily doped N-type substrate as the drain. A lightly doped N-type epitaxial layer is grown on top of it. Within this epitaxial layer, a P-type region and a heavily doped N-type source region are formed through doping. Finally, a V-shaped groove is etched vertically using photolithography. A layer of silicon dioxide is grown on the surface of the groove, followed by a layer of aluminum metal, forming the gate electrode. The N+ type source region is shorted to the P-type region through a metal electrode. When the gate-to-source voltage exceeds the threshold voltage, an N-type inversion layer forms beneath the gate along the bottom of the V-groove in the P-type region, creating a conductive channel. As you can see, the current path between the source and drain is vertical. Unlike the lateral current flow in low-power MOSFETs we discussed earlier, where carriers move horizontally from source to drain. In addition, the drain region in VMOS devices has a large area, which helps dissipate heat generated by power loss. The channel formed near the P-type region beneath the V-groove is very short, and the channels on both sides of the V-groove are connected in parallel. Multiple V-grooves can also be connected in parallel as needed, allowing large currents to flow through the channels. Moreover, the lightly doped N-type epitaxial layer near the gate can withstand high voltages, significantly increasing the operating voltage range of the VMOS device. Modern VMOS devices can achieve breakdown voltages exceeding 1000 volts, with a maximum continuous operating current of up to 200 amperes. This is the output characteristics of the VMOS transistor 2N6657. It can be seen that when the drain current exceeds 0.2 amperes, a proportional increase in gate source voltage results in a proportional increase in drain current, indicating that the control relationship between gate source voltage and drain current is highly linear, with relatively low nonlinear distortion. The double diffuse MOSFET is commonly referred to as DMOS. It uses a lightly doped N-type semiconductor as the substrate. A heavily doped N-type layer is formed at the bottom of the substrate to provide good contact with the drain. Two separate diffusion processes are performed on the top surface of the substrate. The first diffusion creates a heavily doped P-type body region. The second diffusion forms a heavily doped N-type source region. A layer of silicon dioxide is then deposited on the surface for insulation, and a layer of metal is added on top to form the gate electrode. The source region is also shorted to the P-type body through a metal electrode. When the gate-to-source voltage exceeds the threshold voltage, a short N-type channel forms beneath the gate oxide layer in the P-type body region. As a result, when a drain-to-source voltage is applied, free electrons flow from the source, pass through the channel into the N-type region, and then vertically downward to the drain. Thus, although the channel in a DMOS device is lateral, the current path is vertical. The channel is very short. However, thanks to the presence of a lightly doped N-type substrate, the drain-to-source voltage can withstand high breakdown voltages, typically over 600 volts. In addition, the channel current capacity is also high, capable of handling more than 50 amperes. Similar to MOSFETs, BJTs also have high-power versions. However, the structural difference between high-power and low-power BJTs is not as pronounced as it is in MOSFETs. The maximum operating voltage of a power BJT typically ranges from several hundred volts to over 1000 volts, and the maximum operating current is usually tens of amperes. Compared to BJT power transistors, MOSFETs offer many advantages. MOSFETs are voltage-controlled current devices with extremely high input resistance, requiring very little drive current, which gives them high power gain. In contrast, BJT power transistors require current drive. The effect of temperature on the drain current of a MOSFET varies depending on the gate-to-source voltage, and is typically represented in the form shown in the graph. When the gate-to-source voltage equals the voltage at point A, the temperature coefficient of the drain current is 0. When the gate-to-source voltage is less than the voltage at point A, the temperature coefficient is positive. When it is greater than the voltage at point A, the temperature coefficient is negative. MOSFETs are typically operated in the region where the gate-to-source voltage is greater than point A. Thanks to the negative temperature coefficient of the drain current in this region, MOSFETs inherently exhibit thermal stability without the need for additional stabilization measures. In contrast, the collector current of a BJT always has a positive temperature coefficient, so negative feedback must be introduced to stabilize its operating point. Third, since MOSFETs do not have the minority carrier accumulation effect caused by forward-biased p-n junctions. The switching speed of power MOSFETs is higher than that of power BJTs. The switching time of a BJT power transistor typically ranges from 100 nanoseconds to 1 microsecond, while that of a MOSFET is about 10 to 100 nanoseconds. As a result, high-power MOSFETs are commonly used in high-frequency circuits or switching regulator circuits. The transition frequency, FT, of a VMOS device can reach up to 600 MHz. However, when using power MOSFETs, two important considerations must be kept in mind. 1. Although MOSFETs require almost no DC gate drive current, during dynamic operation, a sufficient gate drive current is still needed to charge and discharge the relatively large input capacitance of the gate. 2. To increase the breakdown voltage of power MOSFETs, a lightly doped N-type layer is typically added between the drain and source, which in turn increases the on-state resistance between the drain and source. After this lesson, you should understand the structures and characteristics of typical power transistors. 1. Integrated power amplifiers have good performance and are easy to use, which has led to their widespread application. 2. Due to the gate input capacitance of MOSFETs, the driver stage must provide sufficient current to charge and discharge this capacitance. Additionally, MOSFETs operate at higher speeds than BJTs, making power MOSFETs especially suitable for switching applications. Power MOSFETs are also commonly used in high-frequency circuits. That concludes our lesson on power transistors. See you.